So graph number 1, and use your calculator if you need to get some points. 0.5x minus 3 and negative x plus 6. And when you go to do that negative in front of the x, make sure you use the negative sign and not the minus sign, because it doesn't like that. Give you a minute to come up with some points. By the way, is the first one going to be an open circle or a closed circle? Open, is it going to be shaded left or arrow left or arrow right? Left. Okay. Second one will be closed. Which direction is it going? To the right. Okay, hopefully you know that already by looking at those two things, and that'll help you as you graph. And while you're doing that, so yes, we have a point of discontinuity at x equals 4. What kind of discontinuity? Remember we had 3 different types? What would you call that one? Yes. From the old Crisscross song. It'll make you jump. That's really old. I know. That's a jump discontinuity. Right? You're traveling along, singing a song, and then boom, man, you just jump. Right? It's not infinite. It's not removable. It's not like there's a hole in the graph, right? It really jumped. Alrighty, so now let's write some limits, because we need to know how to write limits, and we need to refresh our memories. So the limit as x approaches 4 from the right. What's the limit as x approaches 4 from the right? What is it? As you're getting closer and closer to 4 from the right, what's the y value? 2. That's right. You can see you're getting closer and closer to a y value of 2. How about the limit as x approaches 4 from the left? What? -1. Okay, now you write the third limit and tell me what it equals. Write the third limit and tell me what it equals. I gave you the notation for the right and the notation for the left. I want the overall limit. And the limit, oops, sorry, that's a bad looking eye. Just writing my M before my I. The limit as x approaches what? 4 of f of x. See, that's if you can't write that, then you can't write the limit notation. And you need to be able to write the limit notation. So, what does it equal? Doesn't exist. Thank you very much. Because the left and the right don't match. The left and the right don't match. Therefore, the limit is not existing or non-existent. Okay, let's focus our attention on this picture here on number 7. In fact, I'll blow up and just look at the picture. On the one on the left there, I'll give you a hint. There are 2 points of discontinuity. Can you name them? Points of discontinuity, can you name them? Did you name me? Oh, are you saying x equals 0 and x equals 2, or are you saying 0.02? two different ones, right? So you're saying x equals 0 is one of them? I don't think so. Looks like we go right through it. Now, if you're confused about that dot, do you think that that's a removable? No, sorry. We accidentally tricked you. So that was not my intention. But 2 is right. Yeah, there's a jump discontinuity right there. Any others? X equals 1? What's right there? What kind of discontinuity is this one? Horizontals, asymptote, they go like this. It is a vertical asymptote, right? But that still doesn't describe the type of discontinuity. I'm glad you know it's a vertical asymptote. That's good. It's an infinite one, right? The infinite ones either do like this, or like this, or like this, something like that. Those are your infinite ones. Right? You can use those as like self-defense moves, like if you're in a dark alley, just using your skills. Right? Things like this. If you have two attackers that are coming like this. Just trying to help you, okay? So you can survive. I will tell you on number 8, there are 3 points of discontinuity, and you might want to write those equations down just for fun. Yeah, that'd be good. Especially the second one. First one's kind of boring, but the second one, that's interesting. Do you have that second one written down? Yes. Do you have it written down somewhere? You have it written down? Okay. All right, so there are 3 points of discontinuity in this particular picture. Find all 3 of them. There are 3. Find all 3 of them. Okay, talk to your neighbors. See what people think around you. Just live in isolation. Yes, number 8. Slide that down to number 8. I will tell you that 2 of the 3 are extremely obvious, but one of them is not so obvious. Can you name any of them? X equals -4 is what kind of discontinuity? That's a jump, right? At -4, it definitely is jumping. All right, so what's going on with the next? You have another one? X equals -2, what kind is that? Infinite. So you got the 2 obvious ones. What? You started talking to me. No. Why did I tell you that that second equation was going to be interesting? What are you thinking? Mr. Yeah, you got a thought? Ms. Chalk, what you think? What? No? No, I'm not messing with any of oblique. We're not doing any of those oblique asymptotes. Okay? I'm not trying to trick you here. What can you do with, so we've already established -4 and -2. What can you do with that fraction? Factor it. Nice. You better do that now. Factor the numerator, factor the denominator. That's why I had you write it down. Factor the numerator, factor the denominator. What did you do to the numerator? Yes. Okay. Depending on how much money you have, you might take your x to a fancy place or just take it out. I mean, not like in a contractor killer kind of way, okay? We're not condoning that sort of thing, okay? That is horrible. I can't believe you said that. All right, now, what are we doing with the denominator on the bottom? X minus 2 and x plus 2. Okay? And now for the magic moment you've all been waiting for. Cancel out what? The x minus 2's. What did you just find? No. What did you just find? I'll use purple. We did not find an asymptote, folks. We found a hole in the graph. That's right. That's the third type, right? It's not jump. It's not infinite. It's removable. At x equals what? X equals 2. Oh, there was a hole in the graph right there, but you couldn't see it because it was kind of small. Yeah. Yeah, really small. So the question was asked of me second period, how am I going to know if there's a removable? Okay, the algebra is the only way you're going to be able to do that, and I would be looking for something that was factorable. It's going to be a fraction, right? You're going to have something to factor over the top of something else. That's when you know you're going to have something going on that's got a removable discontinuity in it. That's why I told you the first equation was kind of boring, because you're not going to get any kind of removable ones in that. It's just a plain old parabola. Okay. So those are some cool things to review. This also goes by the name step function. Maybe that'll make sense to you in a little bit. Sometimes it can be, on the street they might call it the floor function. Yes, they have terminology for these things on the street. I would not expect you to do this, but for kind of educational purposes, I will make a table. You don't normally have to do this when you're making these graphs, but you haven't ever seen this before, so I don't think you have, unless you're just that cool. So these brackets, or in your calculator it'll say int, and that function would be found if I hit the math button, and then it's under the category NUM. You will find that int function. Okay, so if you need to graph it, you can find it there. But what happens if you, it's sometimes referred to as the greatest integer function, which is kind of misleading to a lot of people because they think greatest meaning rounding up. Okay, that's kind of the idea, but you're coming from below, and so people don't understand that. I would have to draw a vertical scale for you to understand that. If you get it in your mind that you're rounding down to the next integer. Now, do we know what integers are? That's the next question I should possibly ask you. Can you name me any integers? What? I need a number that's an integer. A number that's considered to be in the integers. Yes? 1 is an integer. Sure it is. What else we got? 2. Okay, we can count up to infinity by ones. That would really not help us really understand all of them, but that does get there. That's good because that's like, almost half of them, right? -2, -3, -4, -5, -6. Don't forget 0. Those are all integers. Okay? All right, just kind of keep that in mind. So if I take 0 and I put it in this function and I round it down to the next, or I round it down to the closest integer, guess what? That's still 0. What if I take the decimal 0.1 and I round it down to the integer that's below it? What do you get? Round it down. 0. What about 0.25? Round it down. 0. What about 0.5? Round it down. What about 0.75? Round it down. Man, seems pretty eventful. How about 0.999999999? Round it down. 0. That's weird. 0.9 repeated would also go to 0. Okay, so what happens when I put in a 1? We get 1. Because you can't round it down when it already is an integer. How about 1.1? 1. 1.99. 1. So it's kind of weird. What you're telling me by looking at this kind of chart is starting at 0, 0, every one of these numbers gave me 0 until I got to here. And when I got to here, what happened? It jumped. And once you get past that, oh my goodness, do you see why they call it a step function now? Okay. Okay, it has nothing to do with stepchildren or anything like that. It has everything to do with it looks like a set of stairs. Now this could go on for a long time. So we'll do a little dot, 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 and an arrow. That'll get the idea. Oops. Can it go the other direction? Why, certainly. We can have this thing going on for a long time. Of course, I don't want to do that forever. Dot, 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 arrow. Step function. Now that's the rounding down function. There is another one called the rounding up function. But I'm not going to worry about it right now, at the moment. You get the idea that you would round up. Now, notice something. When you round down, where are the solid dots on these little line segments? Where are the solid dots if you round down? On the left. What do you think happens when you round up? The solid dots move to the right. Oh, by the way, the whole graph shifts up 1 unit. So there's a little bit of a difference there. Okay, but this is one of the basic functions. Now, you might think, I've never seen anything like that. Guess what? You probably have come across it in your lifetime. Have you ever parked a car somewhere in a parking garage? They say things like, for the first 30 minutes, you have to pay such and such a price. For the next 1 hour or part thereof. Notice they throw that phrase in there, or part thereof. So what happens if I'm there 31 minutes? Boom! Jack the price up. Well, yeah, just like a minute ago, it would have cost me this much. Yeah, too bad. Right? They want you to cross that 31, from 30 minutes to 31, because they're pushing that price up. And then if you're there, 91 minutes versus 90 minutes, yep, it's going up again. So step functions happen a lot. Anytime when there's an increase like that and you get a certain amount of time for a certain price, boom, the next level it goes up. What's the domain? Smash the entire graph onto the x-axis. Tell me how much of the x-axis gets covered. Ah, right. Everything does. How about the range? Push everything onto the y-axis. How much of the y-axis gets covered? Be careful, it's not all reals. Okay, you got up 20 seconds to talk to your neighbor and see if you can come up with the range of this thing. Well, if you're saying whole numbers, so that's why I think I know what you're getting at, but technical math definition. So you've got integers, which is this big group, positive and negative. The term whole numbers just covers 0, 1, 2, 3, 4. Well, this had all of those positives and negatives in group. So that's why I have to say integers. Okay, so hopefully, like this group over here figured out, it has to be all the integers. You know, you're -2, you're -1, you're 0, you're 1, you're 2. Okay? You know, one way to say that would be like this. But if you wanted to be really cool at a party, you would probably want to use the symbol for the integers. Kind of like there's a symbol for all reals. Okay? Kind of looks like this. From the German for integers. I'm just kidding about that part, but the Z is used. And I think it's because there's the I is used for, is it imaginaries or irrationals? I'm going to have to check on that one. I think it's used for the imaginaries. Okay? We got too many I's, so they threw in a Z. I know. Kind of weird. Are they making fun of me over there? All right. Increasing. I don't think any of that's increasing, is it? Each one of those little sections is constant, right? Now, I do realize that you're saying that to go from one section to the next is increasing, but because they're each little flat sections, I don't think we can say that those are increasing intervals. They're a bunch of constant intervals. How about we talked about finding local minimums and local maximums. And then from the local mins and local maxes, we choose the absolute mins and absolute maxes. Do we have anything like that? Nope. Guess I should just be putting none for a lot of these things. Bounded? Not. Right, not bounded. Discontinuities. Do you have to pick up your pencil as you draw this? A bunch of times, don't you? Yes. All the integers, right? Every single integer is a point of discontinuity. What's end behavior? This is kind of weird. The limit as x approaches positive infinity. The limit as x approaches negative infinity. What's going on? I'm going to say we're probably going to infinity. That's the DNA thing. Or negative infinity, which is the DNA thing, right? The limits don't exist. One's going to positive, one's going to negative infinity. Do we have any asymptotes on the graph? Any places, any lines that we're getting closer and closer and closer to, but never touching? Nope. None. Symmetry. Ooh. Notice on number 9, it says symmetry do not prove algebraically. Chances are some people would hurt themselves, probably because the idea of it's just a weird thing going on here with this rounding down thing. So look at it. Is it reflection symmetric across the y-axis? That would be an even function. Is it? Can you cut this thing in half right down the y-axis and have a duplicate image on the other side? No. Right? You cut that thing down the middle, there is not going to be anything. There's no duplicate on the other side. How about, can you rotate that thing around the origin and make it land on top of itself and it looks exactly the same? Be careful. If you rotate that thing 180 degrees, this little part right here is going to come over here and it's going to look like this. That's not the same, is it? So, it did not pass the odd test either. So this is definitely a neither situation. Kind of bizarre. What are you going to say about x-intercepts? Wow, I'm looking forward to this question. Ooh, closed or open? She said 0 to 1. So think about that. All right, I'll even show you where she's looking. She's looking right here. Let's get rid of this line and this line and this line. See if I can get rid of that circle maybe. No. Oh, stupid me. All right, I'll just cover it up. Okay, so she's looking at this part right here. So her answer was something about 0 to 1. What do you think? Closed or open? Nice, kid. I like it. Closed on the left, open on the right. Doesn't it make sense when you look at the picture that it's closed on the left, open on the right? The dot's filled in on the left, but not the right. It's beautiful. Okay, so any others that you want? Somebody else mentioned a couple that they wanted me to look at. Somebody was talking to me about this. Were there a couple that we didn't know how to do or need to go over? That'd be a good time to ask me. 6 and 7, you were the one. All right, so 6. I'm just going to go real basic on my graph here. E to the x. I do know that it goes through there. And 1 would be right about there. So we're doing something like this. It's an exponential growth function. Does something like this. How do I know that? Well, it looks like an exponential function. Do you know the value of a? You know the value of a? 1, which is why I put it right there at the y-axis, the y-intercept, right? Okay, how did I know that it was going to be about right there? Because the value of e is approximately what? Oh my goodness, work on this, folks. 2.718. Now, if you do know that from now on, then the sign outside my door is going to make a whole lot more sense to you. Okay? Oh, you'll have to wait till you come in the next time. The key thing you need to know that this is exponential growth is that value right there is larger than 1. Smaller than 1 would make it exponential decay. But, you know. Domain, well, that's obviously negative infinity to infinity. How about the range? Smash that whole thing on the y-axis. What do you got? Zero to infinity. Open, closed. Gotta be both open. How do I know the left side has to be open? How do I know the left side has to be open? It can't touch the asymptote, right? The horizontal asymptote. Excellent. All of it's increasing. Decreasing, none. Was there any other part of it that was really confusing, that particular graph? I mean, or... I mean, once you have the picture, it kind of helps. Was there a part of it that was... Say that again? Oh, see if what you had as far as the picture? Okay. Is there any other part of that somebody else needs? Yes? Boundedness? Okay. Somebody else brought this question to my attention earlier today as well. Is this particular graph bounded below? Is it bounded below? Remember we said if you can draw a horizontal line through the graph such that the graph never goes below that. I can draw a lot of lines that match that. Now the biggest one in the world will be y equals 0, right? Because it's the horizontal asymptote as you mentioned. Okay, so it is definitely bounded below. Is it bounded above? Can you draw a line that never will cross above it? Nope. That thing keeps going up and up and up. Okay, that is exactly what you want your money to do, right there. Question? Okay, so I know that negative infinity is a very dark place, but it's way over that way, okay? So, you know, and I know it's really hard for us to think about getting on a roller coaster because every roller coaster we've ever gotten on in our life has a finite starting point, okay? But it is slowly increasing, slowly increasing, slowly increasing. Once we get towards here, then some interesting things happen. And then, whoosh, man, I'm dying right there because that would not be my favorite roller coaster in the whole wide world. Okay? But at the beginning, it's going super doggone slow, but it's increasing. It's getting farther and farther from that x-axis. Not really fast. It doesn't really take off until it gets closer to the y-axis and beyond. Okay? And then you said something about number 7 in terms of its basic picture. Its basic picture is going to, actually it's going to be the inverse of that one I just drew. And so if you switched x and y, you'd have something that looked kind of like this. That's the basic shape of the natural log function. And so tomorrow, I'm going to sit down here in a minute here and look through the 1 through 51 odds from section 1-3. I don't think all of them, because some of them might pertain to the cosine and sine function and the one graph, the logistic graph. So I'm going to look at it and see if there are some that I can get rid of from there. But that's what you're going to be focusing on maybe tonight and tomorrow. And then Wednesday, we'll be ready for our 1-2, 1-3 test. So we will be ready. If you have questions, don't be one of those kids that waits around and never asks any questions and then expects me to answer around 10 o'clock at night. All right? Probably ain't going to happen. So why don't you ask during the school day when you're at school, not sleeping or at work.